Yo! Welcome to this new episode of the CATIA TV, this time on the topic of model-based systems engineering with Stimulus Engineer. MBSE, Model-Based Systems Engineering, is often understood as addressing only the very early phases of systems development where the key language is SysML. How can you go beyond SysML and extend the benefits of using models to the entire development process and automate activities that are today manual, costly, and difficult for embedded systems developers? MBSE can be extended to the development and the simulation of the detailed functional requirements and to all the functional validation activities, software in the loop, hardware in the loop. So discover our unique end-to-end MBSE solution provided by the combination of CATIA Magic and Stimulus. This webinar will be presented by Yves Genevaux, our expert in cybersystem development. As usual, the CATIA TV webinar will be held here, in the post where you are right now, in our CATIA user community, and it will give you the capacity to interact in live with our subject matter experts throughout the chat. So don't hesitate to watch or rewatch the webinar, and we wish you a very good day.
Hello, I'm Yves. I will take you through a journey through the MBSE offering from Dassault Systèmes, focused on two tools, CATIA Magic for the early phases and CATIA Stimulus for the lower levels of the specification, but also, as you will see, the validation activities. If you look to the traditional V, SysML, as you know, is often used for this handling, for supporting the creative process in the early phases. And that is typically where Dassault Systèmes CATIA Magic is widely used today. When you go to the lower level of the specification, when you have to describe every detail of the expected behavior of the system, that's where CATIA Stimulus takes place. And you will see we have a digital continuity between CATIA Magic and CATIA Stimulus. CATIA Stimulus will be also useful to test automatically that the design model, the implementation model, say a control build model, a Simulink model, implements properly the detailed specification, is compliant with its specification, and it's going to be exactly the same at software level. You will be able to test automatically that the source code meets the spec, even up to the very final validation phase where you have the actual hardware environment where Stimulus can be used to test automatically the log files that have recorded the inputs and outputs that happened during these tests. So we're going to go through all these phases. Another way to represent this is this representation where you see various diagrams helping you to create what the new system is going to be, up to the moment where you have architecture, possibly with several levels of block diagrams. And then that's the moment where we're going to go into Stimulus, bring the architecture into Stimulus, and define the expected behavior of each of the components of the system with state machines and also textual requirements. After implementation, the tests are going to be supported also and automated on a very, very innovative manner at software level and at hardware level. So let's look at what you do in CATIA Magic and the transition to CATIA Stimulus. So here we have a topic that is missile, and the core of the process is the magic grid that will articulate all the different steps of your development. And you're going to start working with the needs, the stakeholder needs. In particular here, we are going to focus on one of them, which is about the integrity of the missile. Next step, the system context, where you express what's the environment of the system, basically. Use cases, it's scenarios that the system is supposed to fulfill. Here, in case of critical failure, we need to abort the mission. And if we double click, we see more details on what's going on, activity diagram with the sequence of functions and that different components are going to do. If we here focus on the monitoring of the missile integrity, you see a more detailed activity diagram where you see exchanges between various subsystems of the missile. Let's go to the architecture. You see here the decomposition of the system, the list of all the subsystems that compose the missile. And if we click here, we'll see an IBD where the internal block diagram, where we see the exchange and the interfaces between the different blocks. This is the touch point with CATIA Stimulus. You're going to export the architecture that you have elaborated with CATIA Magic, and the detail of the behavior of these boxes will be done in state machine and executable requirements in Stimulus. We're now in Stimulus. We are going to import the architecture. This is it, which just comes from CATIA Magic with the signals. So now we are in, we're going to explore the next step, making the detailed specification of the embedded system. Here we have you have a will to be actually complete as much as you can, not to say exhaustive, and many details must be captured. In order to execute this specification made of architecture, possibly state machines, combined with textual requirements, if you want to simulate that, so it means you send stimuli and observe what's going on. So the stimuli are generated from test scenarios, and one test scenario does not need to be deterministic, meaning it can have some undeterminism from which you can generate as many test vectors, as many combination of inputs as you like, and that's automatic. We're going to see that in the demo. So let's see the simulation of a functional specification in Stimulus. So we want to make detailed requirements right first time. We have here a model about an HVAC with, in this block, a set of requirements. It's the control command part of the HVAC. If we go inside, you see a few requirements, textual requirements in Stimulus. They are the model and they are executable. We are using here in green, in the green box, it will be a test scenario to generate the stimuli and execute the architecture that we saw before. So here we click on play. We ask to run 200 executions in one shot. The test scenario generates many slightly different inputs. We can have, you can see in blue the temperature, and in the other diagram, you can see the commands generated from the control command system that can be cool, standby, or heat. You see, there are red arrows corresponding to these vertical line. It means that some requirements are conflicting. So the question is, of course, which one, when? So we open the error message, one click, and you know that at the run 160, there is a conflict between requirements at 180 seconds, and these are the two conflicting requirements. It's really, really automatic. Stimulus will help you also to find the missing requirements, the holes in the spec, as well as the wrong ones, those who do not reflect your intention. Let's continue. After the spec is right, you give that to, say, control build developers, Simulink developers, and they or just do manual coding, and you got an implementation you want to test. Let's look for the first step, which is software in the loop. So you're going to reuse the same test scenario, generating the same stimuli to execute this time the code, whereas the spec is now observing what's going on and will report any violation of the specification, and that process is automatic. Let's see this illustrated with the same HVAC example. Where is it? It's here. So we are radically automating the functional test this way. We have here the same example, version 2 here of the spec, and here an implementation which we want to test. It's compiled code put in a DLL or an FMU generated from, say, Simulink. We have a second version of the specification of the requirements because we found errors before. And we replace with a drag and drop the spec with the implementation. And now we create an observer, we call it controller observer, in which we put the validated specification with the drag and drop. Now we can execute with the same scenario as before, but this time it's going to be the code that is executed. We make 100 executions, 300 steps. We observe. We could observe in the simulation, but simply you see the observer is red. So there is a violation of the spec by the code. Go to the error messages. You're going to see that at the run number 3, the code violates the spec at 260 seconds, and the violated requirement is this one. So it's extremely automatic. Our statement is you don't need to do anything to test that the code meets the spec, actually. So you can perform more tests with less effort and find errors that today, with the manually created tests out of informal requirements, created manually from informal requirements, you might have missed them. So we have now a piece of software that works fine. You put it in the real environment. There is only so much you can observe. So what everybody does is record data from the actual hardware in the loop environment and analyze the data afterwards. Generally, it looks like an Excel sheet, basically, with you have all the signals that you are interested in or on which you want to check some properties, and all the cycles you have actually executed. Load this file into Stimulus, we are actually back to the previous situation. We see in the diagrams here the evolution of various signals. We have the spec observing, and we are going to find any violation, again, of the specification. So if we go here and illustrate that with a short video. So this time we analyze test files. So here we're not going to use a complete spec, but simply one property, pretty complex as you can see, and you'd like to know if or not this complex property has been violated during the tests with the real hardware. So here we have a construct that enable you to fetch the file containing the test results. There were, I think, 10,000 cycles performed. Again, we create an observer in which we drag and drop the property we want to check. And we say, okay, right, do 10,000 steps. So we reproduce, we re-execute exactly what happened in the real environment. And again, we have a violation of the observer. So when was it violated? You add it into the plotter view. There are two violations here. Let's zoom on the first one. On the first one, so we expected alarm 33 to become true, and it does not. It remains false, actually. So there is something wrong that happens in the execution of the system. The second violation, this time it does become true, but in principle, it's probably because it becomes too late. You had to do that within 0.4 seconds, and you did it too late. So all these kind of properties with all these kind of constructs can be checked automatically, and you might not put just one property, but maybe a complete set of requirements in order to verify in one shot many requirements. We're saying that Katia Magic is an amazing environment to master and help your creative process in the early phases of the development of a complex system, and bringing Katia Stimulus after for the detailed level when the objectives are a bit different from what you do in SysML, allows you to aim at a complete detailed specification, and also a radical automation of the tests. If you have any questions, I'll be pleased to answer. Thank you.